All right, well, welcome back, everybody. So today we're going to do a little lecture on geometric series. These are series of the form n equals 0 to infinity of a times r to the n. And specifically, a is the first term of the series, and r is the common ratio. So the big question we want to know is, well, what's the sum? And for which choices of r does the series converge? So let's try to get our hands on the sum. Maybe that'll be goal number one. And really what we mean by the sum is the limit of the sequence of partial sums. That's truly what we mean by the sum of a series. All right, so let's work with this. Okay, so our goal series to work with is a series from n equals 0 to infinity of a times r to the n. So we want to find the sum of that. And so remember the sum is, so the sum, let's call that sum s. That is the limit of S sub n, the sequence of partial sums. So in order to get our hands on that, the first thing we want to do is, well, let's write out S sub n. That's the sum of the first n terms. So S sub n, so that's going to require us to plug in 0, and then add, plug in 1, add, plug in 2, etc. But we only want the first n terms, and we're going to keep in mind that we're starting this at 0, right? So if I plug in 0 for n, that's going to be a times r to the 0. That's exactly a. Now I plug 1 in for n, so that'll be a times r to the 1. Then I plug in 2 for n. So notice here, so maybe I'll plug in 3 for n. So right now I have the first 4 terms. Now the first 4 terms stops here. So the question is, well, what does the nth term look like? And again, keep in mind, we are starting at n equals 0. So the nth term should look like this, a times r to the n minus 1. Again, keeping in mind we started at 0, so this is 0, 1, 2, 3. That would be the nth term. Well, here's the problem we have right now. Taking the limit of this is kind of difficult, right? If I take the limit of this as n goes to infinity, I'm not quite sure what it's equal to, right? We're not in a good position right now to take the limit. That's a problem we have to overcome. So we're going to use kind of a nice trick that we use with finite sums. So what we're going to do is take this and multiply every term by r. You're going to see why that's useful in a moment. Okay, so multiplying every term by r gives us the following. So I should have a times r plus a times r squared plus a times r cubed plus a times r to the fourth plus dot 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 plus a times r to the nth. Okay, so again, just multiplying every term by r. And you might say, well, I'm not in a better position to take the limit. I'd agree with you right now, but here is the clever part. We're going to use something called the subtraction postulate, and that says the following. So if a is equal to b and c is equal to d, then the difference of the left side equals the difference of the right side. And we're going to see why in just a moment this is helpful. And keep in mind, this is our goal. We want to compute this. Okay, so let's take the difference of the left side. And notice when we take the difference of the right sides, we're going to get a bunch of canceling. That's really, really helpful. So just think about what would stay and what would go if I did this minus this. Now this would stay, the a. These would cancel when I subtract. These would cancel when I subtract. These would cancel. This would cancel with the term that's after this one. This would cancel with the term that's before this one. And I'd be left with this. So minus, because we are subtracting, a times r to the n. Okay, so the difference of the lefts equals the difference of the rights. Again, that's the subtraction postulate. So now I think it's a good idea to factor. So let's go ahead and factor. Our goal ultimately right now is to solve for S sub n, and we're hoping to get a form for S sub n in which we can take the limit as n goes to infinity. So now when we solve for n, we've got a much better form. Okay, so I'm going to solve for S sub n by dividing both sides by this quantity 1 minus r. And I have this. Now this is helpful for computing a limit, whereas this was just too much of a mess. It was too complicated when it came to taking the limit. If you wanted to check your work, one thing you could do is you could use a little bit of pre-calculus. You could use long division of polynomials here and convince yourself that this divided by this, and then multiply everything by a, would be exactly this. Okay, so this is useful because we can now compute the limit of this. And so now the limit of S sub n as n goes to infinity is exactly the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. Now this limit is in respect to n. Only n is increasing. Everything else is sort of staying the same. The big question is, because we're thinking about exponentials here, right? For which choices of r would this converge or have a numerical limit as n goes to infinity? If I choose r's that are too large, this will diverge. I mean, if r is 5, 5 to the n tends to infinity as n gets large, so that's not so helpful. So the r's that are helpful are the r's that live between -1 and 1. If I choose any r that lives between -1 and 1 and take the limit as n goes to infinity, this will converge. In fact, it'll converge to 0. For any other choice of r, well, that'll diverge. So I'm going to say that this equals a times 1 minus 0 over 1 minus r, which is exactly a over 1 minus r. But specifically for r between -1 and 1. And sometimes we write this in the following way, with the magnitude of r being less than 1, or the absolute value of r strictly less than 1. Okay, so these two things mean the same thing. So what does this tell us? This gives us the sum of the series. So this is equal to this, but only for these choices of r. So I need to be very, very careful. All right, so let's take a look. Let's try this out. We want to take it for a test spin. So for example, we want to find the sum. And let's say I have this. Now let's sort of keep in mind that the series from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r for r between -1 and 1. Which means this. So yes, it would be sufficient for me to just find the first term in the common ratio, but I want to solve this a bit algebraically. So let's solve this algebraically where we're trying to fit this form. This will be good practice adjusting the index, and this will be useful down the road when we talk about representations of functions as power series. Okay, so yeah, I'm going to solve this. Like I said, I'm not just going to find a and r. I want to solve this a bit more algebraically. So this is n equals 1 to infinity. I've got 1/2 to the n. The first thing I want to do is adjust the index. This is my goal index. I want n equals 0. And we know from our study of series that if the index goes down by 1, then this has to increase by 1. We can kind of convince ourselves that makes sense. Because if I plug 1 in for n here, notice that I get 1/2. Well, if these are equal, I should be able to plug in 0 for n, the starting index, and I should also get 1/2 as my first term. If I plug in 2 here, it's got to be the same thing as plugging in 1 here. So that's good. That's step 1. We've adjusted the index. My next step is I'd like to get the common ratio to the nth power. So let's do a bit more algebra. So by using rules of exponents, here I've got the common ratio to the nth, but to make that legal, I need the common ratio to the first. So notice that when I multiply the same base, I add the exponents, and that really does give me exactly this quantity here. Well, this is really nice because I have exactly the form that we're looking for. I've got the series from n equals 0 to infinity of a times r to the n. So this is exactly a, and this inside is the common ratio r. So this is equal to a times 1 minus r, and so that's equal to a, which we said was 1/2, over 1 minus r, so r we said was 1/2 in this case. And so this is not so bad. So here, it just looks like we have 1/2 over 1/2, but that's exactly 1. And that's the sum of the series, which is really the limit of the sequence of partial sums. And so what does this 1 tell me? Basically says, as I take more and more terms of the series, this is getting closer and closer and closer and closer to 1. All the terms are getting closer and closer and closer to 1. So this one in particular has sort of a nice picture attached to it. So let's kind of show this one geometrically as well. So let's say, for example, let's start with some unit square, perhaps. Now, if I plug in 1 here, the first term is going to be 1/2. So let's represent that with 1/2 of the square. So pretend this is 1/2. So that's like the first term of the series, so 1/2. The second term, if I plug in 2, right, would be 1/4. So there's 1/4. So this would be the first term, this would be the second term. Together, this would be the sum of the first 2 terms. Sometimes we call that S2. So now the third term, if I plug in 3 here, I get 1/8. So 1/8. So 1/8 by itself would be the third term, but together, all 3 of these compose what we call S3, the sum of the first 3 terms. And I can keep going here. If I plug in 4, I'm going to get a 16th. If I plug in 5, I'm going to get 1 over 32. And I can keep going in this way. And you can see this is getting closer and closer and closer and closer the further out I go to 1 complete square. So maybe we want to look at one that's a bit more complicated here. Let's perhaps look at something like this. Let's say we've got the series from n equals 2 to infinity of, let's look at 2 to the n over 3 to the n minus 1. And I know that's geometric because, well, these are exponential, so I'm going to have a common ratio of 2/3. My instructions, of course, are find the sum. Maybe I'll put that down, find the sum. And again, we're taking inspiration from our sum of the geometric series. So The series from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r for exactly these choices of r, and only these choices of r. Keep in mind, for any other choice of r, this series will diverge, aka not have a sum. But here r is equal to 2/3. So we're going to solve this similarly to the last one. So here's our starting series. And the first thing we want to do is adjust the index. Okay, so let's write this starting at index 0, so we fit the form. And remember, if this goes down by 2, both of these n's need to increase by 2. So this will be 2 to the n plus 2, and this will be 3 to the n plus 1. And we can, of course, check. If I plug in 2 here, so let's look at our first term. If I plug in 2 here, this will give me 4 over 3. Right? If I plug in 2, that'll be 4 over 3. And is that the same thing if I plug in 0? Well, if I plug in 0 here, I get 4 over 3. Yes. So we're fine there. So our first goal is taken care of. The next thing we'd like is our common ratio to the nth power. So let's do a bit of algebra to get our common ratio to the nth power. Okay, so we want our common ratio to the nth, but we want to do that in a legal way because we want this to be equal to this. So that means I should multiply this by 2 squared, right, n plus 2, over 3. I'm going to write 1 for emphasis. And then, of course, you can check 3 to the n, that is 3 to the n, that n affects both. 3 to the n times 3 to the first is 3 to the n plus 1. And 2 to the n times 2 to the second is 2 to the n plus 2. So that's good. So we've got this. We've got our common ratio to the nth. And now I'm just going to write this out. Just square the 2. And so that's going to give us 4/3 times 2/3 to the n. So there's our a, there's our r. Okay, so there's our a and there is our r. So let's just note that that's our a. There's our r. And so we can go ahead and fill this in. So this is a over 1 minus r. And so let's see what that gives us. That's going to give us the following. So that's exactly a. So a is 4/3. And r we said was exactly 2/3. A over 1 minus r. So let's see what we notice. So this is 4/3 over, so 1 minus 2/3 is 1/3. The 3's will cancel. You could also multiply by the reciprocal, of course. And I get 4. 4 is the sum of my series here. All right, let's try another one. So let's say we've got the series from n equals 0 to infinity of 1 over 4 to the n minus 1 over 5 to the n. This is a good time to discuss when you're allowed to break up series over addition and subtraction. Now, in order to break this up, you can't just instantly just say, oh, it's the series of the first minus the series of the second. So I would have to converge in both of these in order to break this up. So if I looked at the series of this, I know that this would converge because the common ratio is 1/4, and 1/4 is between -1 and 1, so that's good. If I looked at the series of this, I know that would converge because the common ratio is 1/5, and 1/5 lives between -1 and 1. So I need to check that. So the series would need to converge in both terms in order to split this up. So in this case, I'm absolutely allowed to split this up. Can you think of a case where you wouldn't be allowed to split this up? That's a good thing to keep in mind. So you understand when a property works and when it doesn't. So of course we do this with great care. Okay, so yeah, since both of these sums exist individually, I am allowed to do this. And so now I can rewrite this so it looks a little bit more familiar. This is actually 1/4 quantity to the n. And this right here is exactly 1/5 quantity to the n power. And so what is a? So a is 1 in this case, right? So a is 1. So I've got a over 1 minus r, right? So a over 1 minus r minus, so a over 1 minus r. So we got a little bit of fraction work to do. So this is going to be exactly 3/4, and 1 over means reciprocal. So 1 over 3/4 is 4/3. And so think about this. So 1 minus a fifth is 4/5, and 1 over means reciprocal. So the reciprocal of 4/5 is 5/4. And we mentioned before on this channel that if I want, let's call this a recall, if I want to subtract fractions in this way, of course, suppose the denominators are non-zero, I would have this product, which is a times d, minus this product, which is b times c, over this product, which is b times d. It's a really easy way to subtract or add fractions. So what does that give us? So that gives us exactly the following. So that's this product, which is 16, minus this product, which is 15, over this product, which is 12. So this is 1/12. So that's the sum of our original series. What's sort of the moral of the upshot? Again, in order to split a series up in this way, we have to make sure that it converges in both terms. So let's find the sum of this. Let's say we've got the series from n equals 1 to infinity of, let's look at cosine of, let's say, 1/2 radian to the n. Now you can sort of reason this out a little bit. So you know that 1 radian is about 57 degrees. Half of that would be, well, half of that. So what we could say is that this angle definitely lives in quadrant 1. And so the value of this needs to be between 0 and 1. So that's not a problem. So what does that ultimately mean? It means that my common ratio, which would be this, lives between -1 and 1. So this is a problem in which we could expect a valid sum. So maybe I'll note that. So let's note that 1/2 radian lives between 0 and, let's say, pi over 2. And so cosine of 1/2 lives between -1 and 1. I mean, I could make that sharper if I need to, but that's actually sufficient since we're talking about geometric series. But again, that's the same thing as saying that the magnitude of cosine of 1/2 is less than 1. So what does all this mean? Well, it means that my geometric series formula applies. So this is exactly a over 1 minus r for exactly these r's. So let's start to get this into the form that we're looking for. So we started with this. So we've got the series from n equals 1 to infinity of cosine of 1/2 to the n, but by adjusting the index, we get the following. So this is the series from n equals 0 to infinity. Now remember, if this goes down by 1, this, in fact, every n, if I had more n's, would need to increase by 1. So that's cosine of 1/2 to the n plus 1. And of course, you can check this. If n is 1, I get the same thing as if n were 0 here. So this is taken care of. Our next goal is to fit this form. So by doing a little bit of algebra, we get the following. So I can split this up into cosine of 1/2 to the n times cosine of 1/2. So this turns out to be my a. This turns out to be my r. So I've got a over 1 minus r, and that's cosine of 1/2 radian over 1 minus cosine of 1/2 radian. I think that's about the nicest we can do for that. So that would be the sum of our series. The next thing we can do, which is quite interesting, is that we can express a repeating decimal as a ratio of two integers. So let's actually try that. Let's see how a geometric series can be helpful here. So I'm going to say express the repeating decimal as the ratio of two integers. Now, the first key here is we want to rewrite this, and then we want to take note of place value. So what do we mean by this notation? Well, what we mean by this is exactly 0.434343, etc. This pattern repeats forever. Okay, well, that seems fine. So let's see if we can write this as an infinite sum, aka as a series. Well, if I want to write this as a sum, notice that the first sort of bit of repetition stops in the hundreds place. So for this portion right here, that's 43 over 100. I could also write that as 43 over 10 squared, but I'd actually have to do a little bit more work at the end if I did that. If I realized that as 43 over 100, which I understand 110 squared are the same thing, but in terms of algebra, there'd be a little bit more trickiness if I kept it like that. But if I read it in this way, it might be a little bit easier at the end. So what I could do now is sort of think about the repetition occurring in these different little chunks of 100. So here's the hundredths place. This would be 100 to the second power place. So right here, this would be 43 over 100 to the first second. And then here, if I think about this would be 100. So in terms of the place value, 100 to the first, second, thirds place, and so on. Notice that we've got this common ratio of 43 over 100. That makes this an infinite geometric series. Okay, so let's generalize the pattern. So this is the series from n equals 1 to infinity of, let's see here, so 43 over 100 to the n. And let's see if that makes sense. So if n equals 1, do I recover this first term? In fact, I do, right? If n is equal to 1, I get 43 over 100, so that's nice. If n is equal to 2, do I recover this term? In fact, I do, right? If n is 2, I get exactly this. So it seems like we've generalized the pattern nicely in our notation. And so our next goal is to recall the sum of a geometric series, which is exactly this for these choices of R. Okay, so let's adjust the index. Remember, if this goes down by 1, then all of the n's will increase by 1. So this is taken care of, and now we've got to do a little bit of algebra to take care of this, and then ultimately this. So let's rewrite this. Okay, so I've got that, and so what's left over so that this would equal this? Well, I'd need a 43 over 100. So that seems pretty good, and you can easily convince yourself that this is exactly this. Okay, I think I'm just going to rewrite that. I think that would be helpful. So this is 43 over 100 times 1 over 100 to the n. And this is nice because this is exactly our A, and this is exactly our R. And so this is equal to A over 1 minus R. And that's exactly 43 over 100 minus 1 over 100. So this is 43 over 100 over 99 over 100. Notice that the 100s will cancel, and that gives us 43 over 99. So we're able to express our repeating decimal as the ratio of two integers. Okay, so let's do one more repeating decimal question. It's one of my favorites. And so in this one, let's express 0.9 repeating as the ratio of two integers. So the first thing we want to do is remember what we mean by this notation. So 0.9 repeating, this is equal to 0.9999, etc. But we're going to deal with this with, again, place value. And so the repetition seems to stop here. So here, this is in the, or at least one piece of the repetition. So this is 9 over 10 plus, now if I look at this, this would be 9 over 10 to the first second power plus this right here would be 9 over 10 to the first, second, third power. Again, thinking about this in terms of place value. And this would be 9 over 10 to the first, second, third, fourth power. And then don't forget plus dot 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 because this is indeed infinite. And so again, we're going to write this in our summation notation. So this is the series from n equals 1 to infinity of 9 over 10 to the n. And as always, we want to keep in mind this is equal to this for exactly these choices of R. So that means I want to adjust the index. So let's adjust the index to start at 0. And remember, if this goes down by 1, the ends will increase by 1. And so now I want to break this up in such a way that it sort of mimics this idea. So what could we do? We could have 9/10 times 1 over 10 to the n. Well, that seems promising because we can write that in our form. So this is 9/10 times 1/10 to the n. So this is exactly in this form. So that means we're allowed to use our formula. And so, of course, this is equal to a over 1 minus r, but this is a. And this right here is r. Well, this is equal to 9/10 over 9/10, and that's equal to 1, but we wanted to express that as the ratio of integers, so we could write it like that. But that's actually really, really fascinating. This is one of those things that drew me to mathematics. So it turns out that 0.9 repeating is exactly equal to 1, identically equal. Really, really cool. And sometimes people will say, oh, that can't be, they're not equal. Well, I look at it like this. So suppose they weren't equal, right? Keep in mind that between any two real numbers, there's an infinite amount of real numbers, right? That's always true. It doesn't matter how close they are, right? So if I've got two real numbers, even if it's like 0.00001 and 0.0001, etc., no matter how close the two real numbers are, I can always find infinitely many between them. Well, if these two numbers are not equal, then find me just one number that's between them. I bet you can't. Cool, right? So cool.